Okay, well, congratulations, because you have finished Unit 1. That's pretty awesome. And to begin Unit 2, Unit 2 is called, it's called Similarity, Right Triangles, and Trigonometry. Wait a minute, sorry. Similarity Proof and Trigonometry. Similarity Proof and Trigonometry. So, and this is going to begin by us discovering a little bit about some dilations. Okay, so we learned about dilations before. We kind of saw what they were, but now we're going to kind of get real formal about their definition. So what I've got here, I'll see that in a minute. We'll go to that in a minute. But we got here just a triangle, and we've got a point outside of the triangle. Now the point could be anywhere, but this point we're going to call the center of the dilation. Okay, so it is our center right here. Okay, so what we do to construct a dilation is that we measure the distance. I'm going to label these. This will be our center here, but these points, I'll call these, let's see, I'll call this A, B, and C. And my center, I'll just call that P, point P. Okay, so now what happens is, to perform a dilation, you have to know two things. So we have to know where is the center, right? Where is the center? And then we also have to know, what is the scale factor for the dilation. So there is a scale factor in the dilation here. We got to figure that out too. So what I'm going to do is I'm going to do a dilation. I'm just going to do a basic dilation. And the scale factor, which is generally given as the letter K, that's just what mathematicians use, so that's K, is going to be, I'm going to say, it's going to be 2. Okay, and we'll talk a little bit more about the scale factor in a minute. So now that we know these two things, we can actually perform a dilation. So what do we need to do to perform it? Okay, so the first thing we're going to do, number one, is we're going to draw a line, I'll just say draw a ray through each point, or we could call it a vertex in the case that it's a angle, involves an angle, all right, from the center. So I would say, okay, I'm going to be dilating this triangle, so I'm going to draw a ray that goes from that center and through each of those points that I'm going to dilate. So let's get that there. Okay, so now we know that these points after the dilation are going to end up on these rays somewhere. So the second step now is that we have to take measurements Okay, we're going to take measurements from the center to the point in the pre-image. I'm going to use that term because this is a transformation, and we're going to end up, with an image. So that means I'm going to take the measurements from the point to the pre-image. So I made this on purpose so it'd be easy for me, but as you can maybe see here, from our point to A, that is 1 centimeter. So I will write here from, I'll say from P, the measure of PA equals 1 centimeter, okay? Then the next step is find the new measure by multiplying the old measure times k. Well, we said k is going to be our scale factor. So if PA is equal to 1 centimeter, I can multiply by k, right? So I'm multiplying by k, and k in this case we defined as 2. So PA prime is going to equal 2 centimeters. And then I can, my last step is to mark my new point or vertex, right? And it gets marked on the ray. So here I go from my vertex to here was 1 centimeter. Now I'm going to line it up and get it right on that line, that ray that we created, and mark it at 2 centimeters. Okay. And I'll pause that here and I'll finish this up with the other. Okay, so as you can see, I've measured each one of these out, and I doubled, then I multiplied the measurement times 2, and I marked on the ray, and I've completed my dilation here. And what we really, want to kind of be aware of is that dilations, leave two figures similar to one another. So that's really what we're going to kind of talk about for a minute here. What does it mean to be similar? So basically, to be similar means that once you do, what it means to be similar is that if you have two objects that have only been through a similarity transformation like a dilation, they're going to be similar. That's the basic definition. But what is a similarity transformation? Well, an example right now, this one we're talking about, is a dilation. And what it does is it preserves angle measure, right? It's got to preserve all the angle measures here, right? It's got to preserve what we call betweenness. So what that means is that, you're not doing something that's going to then put point B in between over here on C. So everything is lined up in the same order. And they call that betweenness sometimes, okay? And then we have the last criteria is that it has to preserve collinearity. So now we're going to notice something really interesting. I'll just dilate real quick. I'm going to try and do this very, very quickly. Do a rough dilation here. If I were to take and dilate a line from a point not on the line, and let's say I gave it a scale factor of, let's say 3, okay? So the scale factor is 3. I want you to stop and think for a moment. I'm going to, the steps now. I'm going to be measuring the distance from my center here, right, my center point. I'm going to be measuring my distance from there just to that line. What is the next line going to look like? Okay, how much longer is it going to be? Now you think about that for a minute, and I'm going to show you exactly how that works in Geogebra. Okay, so here we have a segment, and we're going to place a point near it, okay, and we're going to dilate that point. And so we'll use our transformations menu here, and we're going to dilate it. So we're going to select the object to dilate. That is, our segment is, better hit escape. You saw that again. Point was already highlighted before I started this. So we start by saying, okay, we're going to dilate the segment by the point C. And then we're going to, did it select it? No, go at point C. And now we're going to enter the factor. So if I enter 3 and hit enter, okay, you can tell that what would have happened, and we'll go ahead and verify all of this. This segment from C to B, which measures 0.89, this new segment is going to be equal to 268, which is 3 times 0.89 roughly, accounting for rounding there. And the same thing here. This would be 3.69 is 3 times, but with rounding that's going on here, we have the same thing. But another thing to notice is the lengths of the segments. So I want you to notice this. If I take off, let's see, and get rid of some of these segments here that we're not going to be looking at. We'll just look at the 2 original segments here. Okay, this segment had a length, and its length is, let's see, that is 1.91. Okay, so what would that be times 3? Well, it would be 5.73. And, accounting for rounding, you can see that the length of this segment is 5.72. So it is roughly 3 times. And actually, it is exactly 3 times. These numbers are the rough numbers. They're not exact numbers. Okay, so it is exactly 3 times. So this is what the scale does, right? The scale factor not only increases the distance away from the center point by a factor of 3, but it's also just increasing the size of the object itself by a factor of 3. Okay? I want you to consider one more transformation here. We're going to make one more dilation. We're going to make a dilation, and we'll do 2 more real quick. We're going to dilate this line by this, with that as the center, and let's just make it simple as a factor of 2. Well, what you're going to notice is that, it doesn't really matter that we had these points D and E here. D and E become irrelevant when we're talking about an entire line. Because remember, when we dilate, we're actually dilating every point on the segment. It's just convenient for us to dilate the endpoints and connect. That's the convenient way to do it. But when you're doing a line goes forever. I mean, the line just doesn't stop. It just goes. And we can zoom out here, and we can just keep zooming, and we'll find out those lines, man, they never stop. They just go and go and go, right? So anyway, when we're dilating a line, what we're really doing is just kind of pushing the line out, right? And if we make a perpendicular line here, let's make a perpendicular that goes through there, and we measure the distances. So I'm going to find my intersections here and there. And now if I measure the distances from our center to the first line and our center to the second line, guess what? It's going to be equal exactly the ratio of the distance from here to center and there to center is going to equal 2 exactly. So we can measure our distances, and actually they're already there, aren't they? Let's see. Oh no, we haven't created these segments yet. Let's just create the segments and then we'll see. So the new measurement is 2.46. So the old measurement we're going to say is 1.23, or approximately that. We create the segment and we can see it, 1.23, and there it is. Okay, so by constructing the perpendicular, we can see the entire line has shifted away. Now notice it doesn't bend in any way, right? I mean, you would think that it should bend somehow, because if I continued along this line, you might think that there is no bending when we are moving the line. Now dilating the line. Now the last thing we're going to do real quick, this has to be super fast, but I'm sure you can already figure this out. What happens if I dilate a point that is on the line? So I'm going to dilate a line. Oops, let me hit escape. Dilate the line by the point that's on the line, and I can make it a factor of whatever. I'll just make it 5. Notice what we have there. We got a new line, but it's the same line. There's no change to it. So that's important to notice, that if a point is on line, you dilate the line, that line is not moving. Okay?